So today we'll be covering introduction to deep learning. So we've learned about data science, recommender systems, machine learning, and all of that interesting stuff. So today, I would be taking a quote unquote gentle introduction to deep learning, because a lot of the concepts within deep learning can get really complex really fast. So the idea of this is just to gently introduce everyone to deep learning. I'm still learning about deep learning, and I hope this is as educational as it is for you, as it would be for me
Hi,
too.
Femi.
Yeah, so today we'll just be having like a gentle, I'm taking a gentle introduction to deep learning. So yeah, just laying out the agenda. So the presentation is consists of four blocks. So first I'll be taking a short introduction, expect it to take 15 minutes. Then we'll go into neural networks, which will take the longest. Then we'll go into specialized neural network architectures, the different special neural network architectures, and finally, applications of deep learning in data science. And the idea is for every block, we just take like maybe 5 to 7 minutes break. So there's a quiz at the end of each block, and there's just maybe one or two questions for each block. And the idea is to kind of get everyone engaged. So for each, at the end of each block, you just help me share your answers on the chat box. Obviously without well, you don't have the slides, so yeah, you'd have to pay attention. And yeah, I think it's very helpful if you can answer the questions. They're very simple questions. If you pay attention, you'll be able to answer the questions. And thankfully, the blocks are not. I'm not going to take too much time. It's only the second block that will take only 30 minutes. So yeah, that's how we're going to go about this, and I think we're good to go. Right. So deep learning, deep learning, deep learning. What is deep learning? So first off, I mean, the first question that comes to mind is, how is deep learning? How is it different from machine learning? We've learned about machine learning. How is deep learning any different? They both have learning in their names. How is it different? So actually, deep learning is a subfield of machine learning. So the way you have machine learning, you are training computers or machines to be able to identify patterns in data. Deep learning is a subfield of that general field of machine learning. And It's different from traditional machine learning. So for traditional machine learning, you have logistic regression, linear regression, decision trees, support vector machines, random forest, KNN, and so on and so forth, which I believe has been covered in previous lectures. But deep learning is different in the sense that it focuses on artificial neural networks and the application to solving complex problems. So yes, we've learned about traditional ML, we've learned about all these different nice algorithms and how they solve problems. But there are certain problems that traditional machine learning algorithms simply fail at. Not because they are not good enough, but because the problem requires some level of complexity and also huge tons of data to be able to solve those problems. So in those kind of cases, traditional machine learning typically fails. But recently neural networks have proven to be very useful in solving these complex problems that traditional machine learning algorithms might not be able to solve. So next question obviously is, why is deep learning the special one? Why is it the one that is going to save us, and where traditional ML fails, why is deep learning the answer? And I mean, there's several answers to that question, but I'll just focus on three answers. So the first is automatic feature extraction. So forget the big English, right? As you've learned in machine learning, there are different steps to building a machine learning model. You need to first define the problem, get your data, pre-process your data, perform some feature engineering. So it's at that feature engineering step for traditional ML, you kind of require some sort of, well, you require human input to be able to look at the data as it is and try to do some feature engineering or create new features out of existing features and feed that into your algorithm. In the case of deep learning, yes, you still need to process your data, you still need to do some cleaning. But for the feature engineering, it's more automatic in the sense that once you're done with cleaning and pre-processing your data and it's in the required format, you can simply pass your data as it is through a deep learning model or a neural network. And the neural network is able to automatically extract features. It's able to automatically identify features that might be useful for the problem that you're trying to solve. So that's what the automatic feature extraction is all about. So in traditional ML, feature engineering it's manual. You need to look at the data, create new features. It's time consuming. But deep learning models can learn these representations. It can learn the representations that we as humans we are trying to find when we are dealing with traditional ML algorithms. And even better is that it can capture complex features without us as humans guiding it. So if you're working on traditional ML, there's a certain level to the number of features, new features that you can create. It's based on your understanding of the domain and the data. Um, where our ability as humans stop to capture features in traditional ML. Deep learning, goes further and it's able to capture really, really complex features without us as humans, explicitly guiding it. So that's the first answer to that question, to why deep learning is special and why it's able to solve problems that traditional ML fails at. The next is its versatility. So it's versatile and it's applicable to different domains. And when I say different domains, I mean domains that traditional ML fails at. At the moment, we use for traditional ML for things like recommender systems, credit risk modeling, fraud detection. These are domains that require some level of human input to create features. You need people with domain knowledge. You need people with knowledge in the credit risk industry to be able to build really good models. You need people with domain knowledge in the credit card in fraud detection industry. You need people with domain knowledge in recommendation systems to be able to build these models. But there's another set of domain where traditional ML fails at, and it's domain where I would say we as humans, it's domains where we have to where like the data has to do with like our sense. So sense of vision, for example. So images, for example, right? We have created machines that can generate image. We have photos being generated like every day. We have speech data being generated every day. As I'm talking right now, it's speech data that is being generated. We have text data that is being generated. For this kind of data that has to do with our senses, whether it's seeing as vision, speaking as speech, listening as speech, also writing as text. Traditional ML might not do as well, but deep learning actually does really well for this kind of domains. And it kind of makes sense because for problems that have to do with computer vision, processing image, for problems that have to do with recognizing speech, for problems that have to do with natural language processing, deep learning is able to extract features that we as human beings we might never be able to extract from the data if we were presented with that data. And I think it goes back to the automatic feature extraction property of deep learning. So it's applicable to these domains, image, speech recognition, and natural language processing because it's able to capture really, really complex features that we as humans might not be able to capture. And finally, improve performance of big data. Yeah, I mean, big data is everyone talks about big data. Every day we are generating data. We live in a very digital world. where the computer is at the center of our lives, whether it's your phone or your laptop or your TV or your smart devices. Data is being generated every second. And the good thing about deep learning models is that it thrives in big data environments. So the more data that you can feed it, it just wants as much data as possible. And it's good for the deep learning models because the more data it's able to get, the more it's able to like capture really complex features. I'm sure like everyone is very familiar with ChatGPT. The reason why ChatGPT is as successful is because it's has been exposed to tons and tons of data, and it's able to learn a lot of complex features that we as humans can't even fathom. It's able to capture all of those complex features on really, really huge data sets, and it's able to create something that is very, very useful for us as humans. So yeah, that's about the improved performance on big data. So these are like the three reasons I would say why deep learning is special. Yeah. So yeah, the next I'll just be going over the fundamental concepts of deep learning. Again, we've all learned about machine learning, so I wouldn't be spending much time here. So the idea is just to kind of refresh everybody on machine learning and how it works. So like I said earlier, deep learning is a subset of machine learning in the sense that it involves the development of algorithms to enable machines to learn patterns in data and make predictions or decisions. The way in machine learning, you need features of the data, let's say, usually represented by X, and using that features to predict a target variable, usually represented by Y. You also have that in deep learning. It's the same way. The same way your model can overfit and underfit, that also applies to deep learning. And it makes sense because deep learning is a subset of machine learning. There are also other concepts that are important and necessary, which I believe was covered in week 8, where I think was an introduction to machine learning. So concepts such as loss functions, gradient descent, learning rates, they're also very, very important to deep learning. So again, I'll be going over all of this because it has been covered. Just a refresher. So now that all this has been said, there's one thing that is kind of fundamental to how it's actually the building block of neural network, and it hasn't exactly been covered. In week 8, it wasn't exactly covered. It was almost covered, but it wasn't. But it's the perceptron. So I think in week 8, there was a section where linear regression was covered, and the other, I would say the brother to the linear regression is logistic regression, and the perceptron is very, very similar to logistic regression, and the perceptron is the building block of neural networks, right? Every other thing you have in neural network builds on top of the perceptron. So yes, just going over the concepts again, you have loss function, which is the difference between the ground truth and the prediction. Is through this loss function that we can know whether our model is doing well or not. If your loss function produces a large value relative to the prediction, then you know that okay, your model is not doing as good. You want the truth to be as close to what your model is predicting. And for classification problems in deep learning, there's more loss functions, but like the major ones is you have the binary cross entropy loss, also known as the logistic loss. I think the logistic loss would be like a beta, it's shorter, so I'll just refer to it as logistic loss. This is used for binary classification. So when you're trying to predict true or false, or whether something is this or that, you use a logistic loss. And you have the softmax loss, used for multi-class classification. So in the event that you are predicting more than one class, so maybe you have like a picture, an image, and you're trying to predict whether it's a cat or a dog or a horse, or I don't know, there's like say maybe up to 5 classes of object that you're trying to predict within the image. That's a multi-class. As long as it's more than 2 classes, it counts as a multi-class. And the loss function for this kind of problems is the softmax loss. And for regression problems, this has actually been covered in the previous classes. Use the mean squared error loss. Again, I wouldn't be going over it just to save time. So if you want to go over this, you can always reference other like the slides from the previous classes. Yeah, just going about the gradient descent. So again, just refresh everyone. Let's say an optimization algorithm is to minimize our loss function. Obviously, our model, we're trying to, what the model is trying to do when you are training your model or when your model is learning, the way it learns is by minimizing the error that it's making when predicting certain values. And just these images, I actually just took them from the previous classes. So just refreshing us again, if you plot your loss against the value of your weight, usually have like, so this is called like a saddle, so to speak. So the idea is it usually starts, somewhere starting from the left. You want your error or you want your loss to be somewhere at the bottom of the saddle. That's what you're trying to do. That's what your optimization algorithm is trying to do. And your gradient descent is moving the loss as the data is learning, as the model is learning. You are trying to move the loss, closer and closer to the bottom of the saddle point. So if you look at the second slide, sorry, the second image, um, you can see the starting point, and the idea is you want to move along the negative gradient down to the bottom of the saddle. So that's where your loss is lowest. And the next concept is the learning rate. So the learning rate is actually that's what determines how the gradient descent algorithm moves fast or moves slow, right? You don't want the gradient descent algorithm to move too fast, because then it might overshoot the minimum, like you can see in the third image. At the same time, you don't want it to move too slow because you just take forever to learn. We want to be as efficient as possible. So we don't want to be too fast, we don't want to be too slow. Like anything in life, you need like some sort of balance. So the learning rate is what is you if you want to adjust how fast or how slow um, your gradient um, your gradient descent algorithm is moving or your loss is reducing. It's the learning rate that you're going to adjust. Yeah, so that's all on the refresher. So this I would spend like some time on. So the perceptron, like I've mentioned, is again it's the simplest form of a neural network. It's the building block of the neural network. Every other thing you have in a neural network builds on top of the perceptron. So if you can understand how the perceptron works and how you can combine these perceptrons to build a neural network, then every other thing would come easy to you. But the fundamental is very, very important. And the perceptron is inspired, by the way biological neuron works in the human brain. So this is not to say that the neural network it works like the way the human brain works. It only draws inspiration from what neuroscientists understand the way our brain works. And the way our brain works, there's billions of neurons in our brain, and there's connections within those neurons. And you can think of each neuron as a decision maker. So what does that mean? So each neuron, right, or a perceptron, I'll use a perceptron in this case. The perceptron is basically a it's like you can think of it like as a block or a function that takes in an input and based on some data that it has, it does some computation and it returns an output. And the output can either be yes or no. So it takes an input and it can say, okay, don't do this or do that. So it's kind of like a decision maker, so to speak. And it's the basic building block of neural networks. So the perceptron works, and I think I'll explain more on this, but just try to follow along. So for the perceptron, you have the inputs, like I mentioned, I can think of the inputs as the features of your data, right? In traditional ML, you have, let's say, you're trying to predict the age of somebody. You can kind of take their weights and their heights. Those are like the features. Those are the inputs that your perceptron will take in, and each input is associated with a weight. So we want to assign a weight to, let's say, your if you're trying to predict your age, right? Obviously, your height and your weight might um they're not going to be equally as important, right? One would be maybe more important in determining your age than the other. So the idea is we want to assign a weight, for a feature that determines more your age. Let's say it's your height that determines more your age. We want to assign a higher weight to that feature, which is your height. And for your weight, we want to assign, maybe your weight doesn't really matter when it comes to determining your age. Then we want to assign is a lower weight to that weight input or feature. And it determines the significance of the input that this perceptron is taking. So that's on the inputs. For the weights, like I said earlier, it represents the strength or the importance of each input. Each input or each feature is not going to determine. So if you have a perceptron, there's different inputs that's coming into the perceptron. Obviously, it's not going to consider each input equally. There's certain inputs that we want to give more importance to, and that's what the weight is. So if you have 10 inputs or 10 features, you'd have 10 weights, which with each weight corresponding to each input. So now we have the inputs, we have the weights, and the weighted sum. So next we find the weighted sum, which is just the result of multiplying each input by its corresponding weight and summing up this product. So there's a little bit of linear algebra going on here. And just to be within the scope of this lecture, I wouldn't go into like the linear algebra of how these inputs and weights are multiplied by each other to get the product. But I can think of it as multiplying x1, which is with the first input, by w1, which is the second input. So you do that for every input and every weight. So multiply the first weight by its own, the first input by its weight, second input by its weight, third input by its weight, and so on. And so when you multiply all of that together, you can now sum everything and you get a weighted sum of this product. Next, you have the activation function. So now, we've taken the input, we've taken the weights, we've combined everything together. We need a way to be able to say, okay, what is going to be the final output of this perceptron? Is it going to be yes or not? Yes or no? Is the perceptron going to fire or not? Is it going to activate or not? And to be able to do that, we need an activation function. And there's different activation functions that we have. There's a sigmoid function, there's a ReLU, and different variations. But again, just to be within the scope, I wouldn't go into the different functions. But I've shared resources at the end of the presentation. So with the fundamental knowledge I'll present here, you can take these courses and it should be much easier. So the activation function is the one that determines whether the perceptron is going to activate or not. Basically, it's saying that, okay, this perceptron is going to give maybe a 0 or a 1, right? We want it to either do something or not. And the output is what represents the output of the activation function. So again, like I said, the perceptron takes in inputs. What you need to understand is that the perceptron takes in inputs and returns an output, on a very, very fundamental level. It's a function. It takes in an input and it returns an output. And the output is what is going to determine if the perceptron, would activate or not. So is the perceptron, is it going to just remain dormant, or is it actually going to contribute to your final response, right? So that's on the perceptron. So just trying to make an example and making it clearer for us. So let's say you have a simple problem, right, of acceptance at the university, right? So you have for every student that wants to get into university, you have two features of them. You have their test scores and their grades. So how do you determine which student to get accepted at the university? So you have student one. Student one has a test score of 9/10, and his grades were 8/10, right? And second student had test score of 3/10, and the second student had grades of 4/10. As you can see, the first student, right, was accepted, but the second student wasn't accepted. So now we're presented with a third student, and the third student has 7/10 tests and 6/10 grade. And on the right, you can kind of see like a graph of other students, the data of other students. So you have, if you plot the grades versus the test scores, you can see other students, you can see the red represents students that were not accepted, and the blue, oh, sorry, yeah, the blue represents students that were accepted. I can see where student one falls in the graph. I can see where student two falls with the graph. So just looking at the data, I mean, I would want, if you can get like people to guess. Oops, sorry. So if we were to guess, you can just put in the chat box, where do you think the student three would fall? Do you think the student three would be accepted or not, right? Again, this is just for you to try. It's just trying to build the intuition. Like, where do you think student three would fall within this graph? Do you think the students will be accepted or, okay, I've gotten first. Okay, accepted, interesting, okay. Maybe just one more answer and I would kind of, okay, it seems like everyone is aligned on that. So it seems like everyone thinks the students will be accepted, right? Um, so I mean, think about it, right? You don't have any prior, like you don't have any, you don't have any model to say, okay, yes, student two will be accepted or rejected. But just by looking at the data, you can already tell, you can tell where this student will fall on the graph, and you can already say, oh, this is where the student is going to fall. Where you can already tell that the student is going to either get accepted or not. So think about that process that you just went through of trying to determine whether the student will be um, accepted or not. Think of that process as what a perceptron is trying to mimic, essentially. That's what the perceptron is trying to do. So you've basically acted in the place of a perceptron and you've tried to um, tell us whether the students will be accepted or not. Now, I mean, in our case, we have, our brains are very, very advanced and complex. But if we were to give this to a simple perceptron, right? What the perceptron is doing, and that's what, people that have answered this question, that's what they're trying to do. Ideally, we are trying to plot a line that divides these two groups of people. And the minute we can place, students three, either on the right side of the line or on the left side of the line, it becomes clear whether the student is accepted or not. And that's essentially what the perceptron is trying to do. So the fundamental question of the perceptron is, yes, there's a line that divides this group, but how do we find that line? So essentially, that's what the perceptron is trying to do. It's trying to find that line that divides, these two classes. And in machine learning problems, there might be more than one class, right, that you're trying to predict. So maybe one line might not suffice, right? Let's say you have three features, you might need a more complex relationship, a more complex line. Maybe not in this case. This is kind of like this is a linear equation, right? You might need something maybe more complex to capture the relationship if you have more than two features. Right now, we're just dealing with grades and tests, so it's easy to draw that line. But in most cases, you have more than two classes, and the relationship might be much more complex than a linear one that we are seeing here. But back to the original question, how do we find this line? This is, basically how we find it. So going back to a little bit of linear algebra, the equation of a line, right? You have this line here. How do you find the line? You go back to what's in the equation of a line. I think this was also covered in previous classes. So what's the equation of a line? Y is equal to mx plus b. If you think about it, right, the test score, which is 7, that's your so for the first feature, for your first x, that's the first weight, so to speak. No, that's the x value rather. That's the x value. So your first x value is the test score, which is 7. Your x2, which is second x value, is 6, right? So you have 6 and you have 7 as the x, right? Now we need weights, like I mentioned, 7 and 6 is the inputs, test and grade is the inputs, but you also need weights to be able to scale. Okay, I want you to pay more attention to grades, I want you to pay more attention to test. And you can see in this equation that test has a weight of 2, while grades has a weight of 1. So multiplying 2 by 7 and 1 by 6, that takes care of the first part of our equation, which is y is equals to mx, right? So you can think of m as your weights and x as your inputs, and the b is just a bias term, and the b is supposed to control like how the line is. So here we have like the equation of a line, and that is how the perceptron is able to make decisions. It's able to, at the end of the day, the perceptron is just trying to draw a line, right, across your data, separate the groups, and make a decision on whether something should occur or not. And this, you can see the equation represented here. And this is a very simple perceptron. It basically says, after I've summed up my weights and my inputs and the bias term, and I've gotten my answer, if my answer is greater than or equals to 0, then get this person to be accepted. Now you can think of this equation as an activation function. So this activation function is just it's called a step function. So if it's greater than 0, yes. If it's less than 0, no. That's the activation function. It's just looking at, okay, is this 0? If it's 0, pass. If it's less than 0, if it's greater than 0, yes. If it's less than 0, no. So this is a step function. It's a very simple activation function. So there's different activation functions. There's step function, there's sigmoid function, there's a ReLU function, but again, we'll not be going into that for now. And on the right-hand side, this is just a mathematical way of representing what we have on the left-hand side. So again, I don't want to go too in-depth into the mathematics here. So, but like I said, you have x1, x2, w1, w2. And for those of us that are familiar with maths and linear algebra, basically on the activation function is just saying sum over all the x, which is all the features that you have, perform this computation, which is multiply their weights by their inputs and add the bias term. And if the output of that equation is greater than 0, give it a yes. If it's lesser than 0, then it's a no. Yes, so neural networks. This is why we're here. So the first section was just handling perceptron, and the section for neural networks build on top of that. So now that we've learned about perceptrons, we can think of a neural network as, like the name implies, it's a network of several perceptrons that takes in inputs and generate the predictions through a series of calculations. So the calculations is what I explained in the previous section, and you do the calculation within the perceptron itself. So you can think of, for each single perceptron in the network, you have to do some calculation, and amongst other perceptrons, you also have to do some calculations amongst those other perceptrons. And the calculation that we did to arrive at the final output, right? We also have to do that calculation, amongst other perceptrons. So in the event that you have in the previous section, we had just one perceptron. We saw how we could generate an output for a single perceptron. But in a neural network, it's a network of perceptrons. So you have different perceptrons. You're not just dealing with just one now, you're dealing with multiple perceptrons. The number can go as high as your model can be complex, right? And the same calculation that we did for within the perceptron, we also have to do that amongst other perceptrons. So you can think of it as the output of one perceptron would be the input into another perceptron. So the neural network is it's a network, or just think of it as a network of several perceptrons. And I would show you how these networks, how they're architected, and some terminologies to be familiar with how neural networks are. So first, like I said, we're not just dealing with one neural network. Now we're dealing with multiple neural networks. So fundamentally, we have to be able to understand how can we combine two perceptrons to come together to give us an output. So if we understand how we can combine two perceptrons, it becomes easier to understand how you can combine multiple perceptrons, because in most neural networks, they are dealing with depending on how complex the neural network is, you can be dealing with as many as 10 perceptrons, 100, 1,000, 10,000, 100,000, maybe a million. Definitely more than a million. So your deep learning model or your neural network can get very, very complex. But before I explain how we can combine the perceptrons, let me just make something clear. If you look at the head of like the slide, you can see what I titled it as is neural networks as multi-layer perceptrons. So you can either refer to it as a neural network or a multi-layer perceptron. So maybe you take a course or you're reading an academic paper, they might refer to it as a multi-layer perceptron. They might refer to it as a neural network. So just know that both terminologies refer to the same thing. And if you think about it, right, with the explanation so far, they're basically the same thing. A neural network, what is it? It's a network of different perceptrons. What is a multi-layer perceptrons? It's a network of it's the same thing. It's a network of perceptrons in a multiple layer. So they're actually the same thing. So back to the original topic. So how do we combine two perceptrons? We've learned how one perceptron can make a decision. So how do you combine these two perceptrons, to be able to make one decision? So if you look at this image I have here, okay. Okay, so if you look at the image I have here, so the first, remember that in the previous section, the way we represented the perceptron is that we first, we had like some data, we plotted X against Y. The red is the not accepted and the blue is the accepted. So let's say the first one here, this is our first model. This is our first perceptron, right? And you can see that the input or the X is 0.7, right? The output of the model or the output of the perceptron in this case is 0.7. How do we arrive at that 0.7? It's essentially by running the inputs and the weights of this particular perceptron through the perceptron. So in this case, we don't have access to the inputs and the features and the weights, the inputs and the weights, or the features and the weights. Because remember, we're looking at a single, like this is the output. I don't know if my cursor is on the image, but for this particular example, it's the output of a perceptron, right? Let's assume that we've already done the calculation that we did previously, and the output is 0.7. For the second image too, let's assume that we've done the calculation and the output of the perceptron is 0.8, right? So we've done the calculation for perceptron A and the output is 0.7. We've done the perceptron for we've done the calculation for perceptron B and the output is 0.8. So now we have two perceptrons with their outputs, right? Remember now that we're trying to combine these two perceptrons. And how does that work? Again, think of the way the perceptron works. It takes an input and you assign a weight to each input and you sum up the value. So the same way a perceptron takes in inputs, it's the same way you can take the output of a perceptron and pass it as an input into another perceptron. So for perceptron A here, the output is 0.7. We can take the output of perceptron A and turn it we can take the output of perceptron A and turn it into an input for this third perceptron. Let's assume that this perceptron C. The same way we have the inputs at 0.7 here, we can have a weight associated with that perceptron. So in this case, 7 is the weight that has been assigned to this perceptron. And for perceptron B also, we've done the calculation, we got some inputs, we got some weights, and the output is 0.8. We can feed the outputs of this perceptron into a third perceptron, let's say perceptron C. And now the output of this perceptron B is the input that this perceptron C is considering. So slowly you can start to see how all of this connects together. So first we dealt with one perceptron where we had an input and the weights. And now we are saying, okay, if we can do that for one perceptron, why can't we combine two perceptrons and feed it into a third perceptron that takes in the output of perceptron A as an input into perceptron C, and the output of perceptron B as an input into perceptron C. And we know very well that for each input into any perceptron, we need a weight. So we say for perceptron A, the weight is 7. For perceptron B, the weight is 5. And the same calculation that we did to come about the output 0.7 and 0.8, the same calculation that we're going to do here. So 7 times 0.7 plus 5 times 0.8, and you add the bias term. So the bias term here is -6 for this perceptron. So calculating all of this together, we get a value we get like 2.9, right? That was the output for this third perceptron. This is where it starts to get interesting. So yes, we've gotten perceptron A, we've gotten perceptron B, we've combined it using perceptron C. So perceptron C takes perceptron A and perceptron B. And we can see that the output is 2.9. And you can see that the next, after this has been computed, we've gotten 2.9. The next, this is another perceptron, right? And we can see that the output, for some reason, it has changed to 0.95. And the reason for that is an activation function there's a new activation function that has been introduced. So remember I talked about activation function, which is supposed to determine what the output would be. In the previous section, the activation function was a step function. It's a simple function that just says, if the output is greater than 0, yes. If the output is less than 0 or equals 0, no. But in this case, we're not using a step function. We're using a sigmoid function. And a sigmoid function is actually what is used in the logistic regression algorithm, but I wouldn't go into that. But you can think of it that, okay, in the previous example, we use step function, but in this example, we're using sigmoid functions. So always have at the back of your mind that there's different step functions that you can use for solving different problems. And in this case, we are using a sigmoid function. What does the sigmoid function do? What does it do? It basically takes, it takes a number and it returns a value between 0 and 1, right? That's how that sigmoid function works, right? It's for any number that you pass to it, right? It would output a number between 0 and 1. That's where the sigmoid function works. For the step function, it's just saying, okay, if it's greater than 0, 1, if it's less than 0, 0. But in this case, the sigmoid function is different and is a little bit more complicated. So it says, if the value, for any value that you pass to the sigmoid function, it will return a value between 0 and 1. And you would see, much later into the slide, how this sigmoid function, is useful in predicting some problems, or if you are trying to predict like a class, typically use the sigmoid function. So yes, we have seen how this perceptron C has taken the input of perceptron A and perceptron B and generated a value 0.95. And if you look at this new perceptron, right, that's been generated. In fact, these are like the same. This is the same perceptron that we have here, right? Because if you look at data, it's kind of like the same. And something interesting actually happens when you pass that data from perceptron C, when you pass it through a sigmoid function, not only does it squeeze the value into like a number between 0 and 1, but you can see that the line is no longer straight, right? So compare this with this, like this is not straight. For the previous perceptrons, you can see a straight line, you can see a straight line. Here you can see it's not a straight line, right? And this is actually something important about deep learning on neural networks. And I explained this in the first slide. It's able to capture complex features or relationships. Like I said earlier, right? Most of the examples I've shared so far, it's kind of like a linear. We've presented a linear solution. What I mean by that is you can easily plot a straight line through your data points and you can separate your classes. But there are certain problems where a linear solution won't just work because the relationship between the data is not linear. I don't know, it could be quadratic, right? I don't want to go really in depth into the maths, but I'll just say some mathematical terms. But if you're familiar with like a quadratic function, it's usually not like a straight line. And there are other kinds of functions that are not linear. So in this case, it's not a straight line. So you can already tell that obviously this is not a linear solution. It's a non-linear solution. And it's very important because what this means is that if you present your neural network with a lot of data, right? And let's say the problem that you're trying to solve is not a linear problem. When I mean it's not a linear problem, it means that we can't just plot a straight line through it, right? Your neural network will be able to capture those really complex problems or capture those complex features or relationship between the data that is not linear. And this is actually very, very, very important to why neural network works where traditional ML fails. Okay, I say polynomial, yes. So you can have, yeah, exactly. So like a polynomial function, for example. So you can see that this non-linearity that has been introduced into the data is very, very important for the way neural network works. So again, just looking at the former, this is still the former, what we had on the previous slide. It's still the same diagram. And I just want everyone to just follow along while I go from point A to point B to point C. These three diagrams that we have here, they are essentially the same thing. But what is happening is, as we are moving from this first image to the second image, so the first image, we have our graph of the perceptron, like the data that is being fed into the perceptron. We have this graph, we have the line, and above we have the equation of the line. So 5x1 minus 2x1 plus 8, this is the equation of the line. Let's see, okay. So we have the first perceptron, we have the graph, we have the equation of the line. The second perceptron, we have the graph of all the data that was fed into that perceptron, and we have the equation of that line above here. So obviously, if you are dealing with a lot of perceptrons, right? Let's say you are dealing with hundreds of perceptrons, 1,000, a million perceptrons, which is, again, just pointing to the fact the way the brain works is billions of perceptrons, working together. Obviously, if we try to visualize that using a graph, that wouldn't make any sense, right? This is not a scalable approach. So what we can do is we can have these diagrams, right, that represent how, like, what a neural network looks like, right? This is the second. So if you look at second image, this is a more reasonable diagram to represent how a neural network is. So if you look at this diagram, this perceptron A, this perceptron B. So -8 is perceptron A. -8 is the output of perceptron A. Sorry, 1 is the output of perceptron B. So for perceptron A, you have x1, x2, and you have 5 here, you have -2, and you have the outputs. Also for perceptron B, you have x1, x2. So because we're dealing with two features, x1, x2, right? So perceptron B, you have the same thing, x1, x2. You have 7, which is the weight, I have minus 3, which is the weight. I have 1, which is the output, right? So obviously this is a more this makes sense to represent your neural network, which is again just combination of different perceptrons. So you have perceptron A here, perceptron B here, and this is the third perceptron that combines perceptron A and perceptron B. And you can see here that perceptron A is being fed into is being fed with this minus 8 is the output, but it's being fed as an input into this perceptron C. And there's a corresponding weight 7. And for perceptron B, the output is 1, and it's being fed as an input into perceptron C, and the corresponding weight is 5. So I'll try to label what we all things we have on this diagram. So this x1, x2, minus 8, minus 6, they are referred to as the nodes of your neural network. So these are the nodes. So x1, x2, x1, x2, 1, minus 8, minus 6. These are nodes. And these are edges. So from x1 to minus 8, we have this 5 attached to the edge. Sorry. We have this 5 attached to the edge, minus 2 attached to the edge, 7, minus 3, 5, 7. So in your node is the usually have like the input and the output values in your nodes. And in your edges, you have the weights, right? So now we have, okay, this node x1, node x2, node minus 8, node minus 6, node 1, node x1, node x2. I have this edge 5, which is connecting x1 to minus 8. We have this edge also, and so on and so forth. So obviously, this is a more reasonable way to represent what we have on the left. But if you think about it, there's still a redundancy, and we can obviously make this more efficient, right? You can make this diagram or this representation of a neural network more efficient. And what we have here on the third diagram is essentially how a neural network is captured. Like that's how it's represented. So think about it. We have x1 and x2, x1 and x2, right? There's no point repeating x1 and x2. So we can just have a single x1 and a single x2. And so x1, x2. So remember we have two perceptrons, right? So we have this is the first one, minus 8 and 1. Now that we have these nodes for perceptron A, this node for perceptron B, we can make use of these edges and say, okay, for all the edges coming from x1 into perceptron A, that's the x1 value for perceptron A. For the edge that's coming from x2 value for perceptron A, right? We can just label that edge with the value. So now we have 5, x1 is going to minus 8, we have 5, x2 is going to minus 8, we have minus 2. So that takes care of the first perceptron, right? x1 is feeding into perceptron A, x2 is feeding into perceptron A. Now coming down to perceptron B, you can see you can see that edge of the x1 is coming into 1, into this perceptron B, and I can see x2 is coming into perceptron B. So 7 is attached to x1. So if you trace it, x1 to 1, you have 7, x2 to 1, you have minus 3. So this is obviously a more efficient way because we have x1, x2. Imagine if we had, if we are considering, let's say, 10 different perceptrons, right? Or 10 different inputs. We're not going to do x1, x2, x1, x2, x1, x2, right? So that's going to be 20 nodes just for the first level. Obviously, we can be more efficient and say, okay, if you just have x1, x2, we can represent in such a way that we can have whatever number of inputs that we have. We have 10 inputs, right? We just need to create just 10 nodes for those inputs. So this, what we have on the third diagram, is how a neural network is represented. And just I'll add one or two things to the terminologies I've said so far. So far, I've talked about the nodes and the edges. So you can think of the nodes as the inputs or inputs and outputs, and you can think of the edges as the weights. So the first, and this points to the fact that it's a multi-layer perceptron. So the first, this x1 and x2 here is referred to as the input layer. So in your neural network, you have, what is called layers. So you have layers in your neural network. So the first, the first nodes that you have here, the X1 and X2, those are referred to as the input layers. Minus 8 and 1, this is another layer. Right, let's say we had X3. If we're dealing with three features, X1, we have X maybe somewhere here and we have X3 here. And the same way we have minus 8 here, we'll have one more node here and we have one here. So this first layer is called the input layer. The second layer, 8 and 1, minus 8 and 1, is called the hidden layer. And this final minus 6, or um, this final layer, which is essentially used to make a decision, would be your output layer. So we have the input layer, we have the hidden layer, I have the output layer. So again, this is just mimicking what a perceptron is. A perceptron has an input and an output. And in between, inside the perceptron, is calculating something using the values of the hidden layer. And for neural networks, you can have more than one hidden layer, which I would explain in the next couple of slides. So again, remember that when we're talking about neural networks, it's a network of different perceptrons. So there is no limit. Well, technically speaking, there is no limit to the number of number of perceptrons that you can have, and there's no limit to the number of connections that you can have to the perceptrons that you have in your neural network. So again, just to build intuition for this, you can think of your neural network as just a combination of so many perceptrons. The perceptrons are taking inputs and trying to make a decision, and the position of this perceptron in this layer would feed into the next layer, and it feeds into the next layer, and it feeds into the next layer until it gets into the output layer. So the more layers that you have, in your network, the more complex it is. It's usually referred to as a deep neural network. So that's where the term deep learning comes from, right? Yes, it's a neural network, right? We can have a neural network with just one layer like we have here, right? But there's cases where you have more than one hidden layer, and you can have up to 10 or 20 hidden layers. So then we have minus 8 and 1 here. We can have several layers that will be considered before we eventually get to the output. So that's where like that term deep learning comes from. So we can have networks that are very, very, very deep. And the deeper your networks, the more complex features they can capture. And again, this goes to my point in the first section where deep learning is able to capture really, really complex relationship in our data that we as humans might never be able to manually see or visualize. So this next slide is just basically, again, explain what I mentioned in the second slide. So we can see here, we have the input layer, which is where your data starts from. You have the hidden layer. I have the output layer. So this is just a simple representation. So a deep neural network, in this case, you have two layers. And like I said, you can have multiple layers. So you can see layer one. And something interesting is happening. As it goes from layer one to layer two, you can see we have a more complex line that is being drawn. And when it gets to the final layer, you can see this is just so complex. Like, what is this? So again, that's just like where the term deep learning comes from. The more deeper it gets, right, the more complex relationships you can pick out. I can see that the more complex it gets, the more it's able to better separate the data. But again, like you've learned, obviously you don't want your data to overfit to the problem. So there's the way you can use regularization and other techniques, the same way you can use it for neural networks. But I don't want to go out of scope for this, so I'll just try to cover the basics. So like I mentioned again in the first section, so you can look at this neural network. You have the first input layer. This one is the bias term. This is another hidden layer. This is okay, input layer, hidden layer. You can see for the hidden layer, it's a sigmoid function that is being used. Here you have a sigmoid function in hidden layer one. In hidden layer two, you have a sigmoid function. In the final layer, you have a sigmoid function. And for this neural network, this is a neural network essentially. It's trying to predict the probability of this class, whether it's a gift or not, whether it's a gift box or not. So in this one is a binary classification, which is just one. And for this, we use logistic loss. But there are cases where you are trying to predict more than one class. You can also use neural network for that. So you have probability of whether it's a duck or I think it's a beaver, not sure, or a bunny, I don't know. Pardon me. And I don't know what this last animal is, but essentially you can have like more than one class, right? And you can use, depending on the number of classes that you can have, you just add, you know, a perceptron for each class. And instead of using a logistic loss or a binary, um, instead of using a logistic loss, you can use a softmax loss. Remember, I said for multi-class, you can use a softmax loss, which is binary cosine entropy loss. So yeah, this just building on what I mentioned before. So yes, we have our neural network. We know there's the input layer, there's the hidden layer, there's the output layer. So like I said, the perceptron, the way you have computation within the perceptron, the same way you have to do that computation amongst all the perceptrons that you have. And how that computation is being done, starting from the input layer down to the last layer, which is the output layer. Starting from the, you want to do your computation starting from the input layer, through all the hidden layers that you have, and then to the final output layer. And the process of performing that computation to get your output, which is your prediction, that process is called a feed forward. So feed forward, like the name implies, they're just feeding, like you have your network already initialized. They're just trying to feed your data forward through the network and generate like all of these different values. So feed forward is the way this mechanism works. And obviously, if you want to generate like your output, you have to do like a feed forward. And what I have on the right here is just representing the way the maths works. I don't want to, I mean, I've been saying I don't want to go too in depth into the maths, but it's hard to explain this concept without bringing some form of math into it. So just pardon with me if math is not your best, if it's not your, um, if it's not something you enjoy so much, but I think this is like maybe a simple enough representation. So I'm just looking at, so what are we trying to do with our network? We're trying to generate an output, and Y is usually what you represent as the output of any, not just a neural network, for any machine learning model, right? The target variable is your Y. And in this case, it's a Y hat. Y hat is usually the predicted value, while your Y is the actual value. Remember, we're comparing the ground truth, which is Y, against the predicted value, which is Y hat. So to get the Y hat, this equation is basically collapsing what we have in this neural network into this bunch of matrices. So starting from, our feed forward is from left to right. So let's consider this from, in this case, from the right to left. So x1, x2, you put all your inputs, all the data from your input layer into this matrix, right? Just simple one by one matrix. In the second matrix, right, you would put like all the weights and all the inputs for your hidden layer. So in this case, okay, there's one hidden layer, but you can see from the inputs into the hidden layer, we have the first set of weights from the inputs into the hidden layer. So that represents this first column. This first column. Yes, this first column. And this second set of weights that we have here that feeds from the hidden layer to the output layer is the second. That's what we have on the second column here. So you can see this giant matrix. It's just representing the weights that we have. And from the weight of the first layer, right? So, and the weights, okay, actually I missed this step there. So again, sorry, pardon me. This 2x3 matrix that we have here is looking at the weights from the input layer and the weights going into the output layer, into the hidden layer. So the input layer comes with some weights, and the hidden layer also gets like some weights. So this giant 2x3 matrix is considering the weights from the input layer and into the hidden layer. And the final matrix that we have here is just the 1x3 matrix, and capturing the weights that we have in that is coming from the hidden layer into the output layer. And you can see this sign that we have here. This is the sign for the sigmoid function and the activation function, the sigmoid function. So after calculating all of these values, you still have to pass it through a sigmoid function. So you see that here, sigmoid function, do that sigmoid function. So that's essentially what that equation is. And you can further collapse it and say, okay, you just want this first matrix to be represented as X, this first matrix to be represented as W, and this last matrix to be represented as W superscript 2. And yeah, this makes sense because if you have like a lot of perceptrons to consider in your neural network, you're not going to be writing all this. It's going to get really bulky really fast. So you need an efficient way to represent, all of this in mathematical terms. That's what is represented here. So this is the, okay. So now we have everything we need. We understand perceptrons, we understand neural network. And what we've talked about so far is how can we set up the neural network and how can we perform this computation. But like we have learned so far, to be able to train a model, you need to be able to compare what your model is predicting versus the actual value. Now, Feedforward is it's going to generate an output for you. But you need a way to be able to compare that output and say, okay, maybe the output was supposed to be 50, but my model outputs 25. Obviously, you want to get that number closer to 50. So what do you do? We've already done the first Feedforward. To be able to do that, you need to do like a back propagation, right? And the way you have Feedforward first, you need to be able to back propagate from the output layer back to the input layer. And that process of back propagating from the output layer to the input layer is that process called like the back propagation. And it's through this back propagation that your model actually learns. That's where the learning actually happens, because it's at that point that it's able to say, okay, I predicted this. I did like the first feedforward operation, and let's say I got a value of 25 when it was actually 50. So the model has to find a way to go back to the input layer and say, okay, using all the weights and all the inputs, we're not able to get the desired results. How do we adjust the weights so that when I'm doing a feed forward again, we can get that 25 closer to 50. So if you do the first feed forward, you get 25, right? But the actual value is 50. You need to go back. So using back propagation and especially try to adjust the weight such that when I do the feed forward again, I can get closer to 50, right? So maybe on the second feed forward, I get like let's say 35. That's getting me closer to 50. And there's something important that is happening here that I would want everyone to pay attention to, and it's the fact that the way we've learned about gradient descent and learning rates, this is actually very, very important to. It's important to like the way the back propagation um, mechanism works. So remember that when you're training your model, you need an optimization algorithm to be able to compare your loss function and say, okay, this is the difference between my predicted value and the desired results. So it's through gradient descent that you can actually reduce your loss function. So back propagation also it takes it like it uses that idea of gradient descent reducing your loss function. And if you remember how like gradient descent works, it takes like the derivative of the functions that was used to derive the prediction, takes the derivative. Again, this is it's some maths, but you can't really escape the maths when it comes to like machine learning and deep learning. So you calculate the derivative and you try to go down. Let me just go back to that slide to illustrate the gradient descent. Yes, exactly. So yeah, you can see gradient descent is supposed to reduce the loss, down to the minimum, right? And what you're taking is, yeah, what you're doing is that you're taking the gradients, or you're taking the derivative of the function that was used to generate those predictions, and you're trying to go like in a negative direction so that you can come to this middle point, right? So that's derivative of the function that was used to derive that was used to generate that prediction. That's essentially what is happening when you're doing back propagation. So remember, for the neural networks, we use the sigmoid function to generate like the predictions at the final output, right? So backpropagation, what it essentially does is that it takes the derivative of those sigmoid function across the different neural networks, and this is possible because of the chain rule. But I don't want to go like too deep into the math. But just think of it as the reason why we can backpropagate through our network is because, or the reason why we have to backpropagate through our network is that we have to somehow find the minimal loss. And to do that, we need gradient descent. And to do gradient descent, we need to find the derivative. So for that backpropagation mechanism, we need to find the derivative of each sigmoid function that was used initially. So you go back across the neural network, um, calculate the derivative, and you have to update the weight. So as they are moving from one layer to another layer, back to the input layer, you are also updating the weight so that when I'm coming forward again, I'm using updated weights to generate my prediction. And that updated weight hopefully would lead to a better result, right? So in this case, I've done my feed forward, I got 25. I'm going back in time. I want to, update. I want to minimize my error or minimize my loss, and I want to be able to update the weight as I'm doing it, so that when I'm coming forward, when I'm doing a feed forward again, when I'm generating the prediction this time around, I'm using the updated weights. And this updated weights was updated because that's what is supposed to reduce the loss. So when I'm doing the feed forward again, it's supposed to take me closer to my desired output, which is 50. So let's say I do that, come back again. The next time I do it, I get to 35. I do that again. Next time I do it, I get to 45. So you can go back and forth. So that's back and forth, do a feed forward, then back propagation. It's called an epoch, epoch. So it's called an epoch. So for each, you're able to move through your data back and forth. So for every back and forth movement through your data, it's called an epoch. So for deep learning or neural networks models, you can do as many epochs as you want, as many that is required to get you to your desired result. So that's the fundamental way like neural network works. This is okay. So I see question you can have his hands up. Okay, I think we can just take that question real quick.
Sorry, I wanted to get to, you said that an epoch is like the forward propagation and then the backward propagation. Like that's one epoch, or is it?
Yes,
Okay.
yes. So the back and forth movement. So you can do that as many times as is required to get you closer to the desired output or desired Y, what you're trying to predict for. So that's in essence. I mean, there's still a lot more that goes into it, but I think this is the fundamental base building block of how neural networks are organized and how they're able to learn, and why they are much suited for some tasks. So that's like that's where neural networks work. So but yeah, we just have one question in the quiz section here. Here we won't be taking a break. I'll just move in straight into the next section. Then we'll take a break after that. So, but this question, I think we can just maybe have like 1 or 2 minutes, have people answer. So, what operation is this for updating the weights of a neural network in order to make the model feel good? Make the model good, rather. Okay, so we've talked about neural network and the different, like how the architecture is, right? How a neural network is combination of perceptrons. You have the input layer, hidden layer, output layer, feed forward, back propagation, doing epochs over your data. So yes, we've learned about neural networks, so that's great. So it's actually specialized neural network architectures for different problems. So remember I said we can apply neural networks or deep learning for solving problems in maybe image recognition, computer vision tasks, natural language processing, understanding speech data, understanding text, all of that interesting stuff. So at the fundamental of those interesting models is the neural network, but the architectures are a bit different, depending on the problem you're trying to solve. So the architecture for an image recognition model will be different from the architecture of a speech recognition model because of the nature of the problem and the way the neural network is organized. But fundamentally, the neural network architecture still remains. Maybe just a little bit of tweaking. So I'll start with the CNNs or the convolutional neural networks. So the convolutional neural networks are the type of neural network that is used in computer vision tasks. So for image recognition or image segmentation. Again, it's inspired by the way the human brain processes visual information. So in the way you have input layers, output layers, hidden layers, the same way you have it in a convolutional neural network. But remember that for images, the data might be different in the sense that you are dealing with data in RGB format. So if you ever had to work with image data, I mean, if you take a photo and you save it on your system, it's either save as a JPEG or a PNG or whatever formats are out there. But fundamentally, it's just separating your image into different color channels. So you have the red, green, and blue channel. At least for the basic photos that we have. So we need to be able to convert that data that is in RGB format into a structure that makes sense, to a neural network. So for that reason, we're not just going to be having, yes, we have input layers, we have hidden layers, we have output layers, but like there is some layer that we need to have that would essentially pass like that image data into a more standard format that your neural network can make sense of. And that format is called, so there's the convolution layer. The convolution layer is at the heart of understanding image data. Um, so you have your input image, this is the image of a dog. To be able to process that image of a dog, you need to apply a convolution layer that takes into account the different color channels. So you can see that you have 1, 2, 3 kind of blocks here. So I'm assuming like each block represents a color channel. So you have RGB, and essentially you're just trying to there's some operations that is going on. I don't want to move out of scope for this, but just think of it as, because it's an image and because of the way image data is stored, there's some filtering that needs to be done. There's a way the convolution layer works. So I wouldn't go into the specifics, but just know that for image recognition tasks or computer vision tasks, we need convolution layers that takes care of the specifics of image data. So there's a lot happening, moving through the data, strides, padding, filtering, and so on and so forth. So we don't need to go into that, but also that, yes, we have these layers. The way we have input layers, hidden layers, and output layers. We have the convolution layer, and we have this ReLU layer, which is supposed to process like the output of the convolution layer. There's also the pooling layer. What this pooling layer does is just to reduce, I'll say reduce redundancies in the image data. So for image data, it can tend to be very, very large because for a single picture, it can be maybe 256 by 256, for example, depending on the resolution of the image, right? For high resolution images, the data will be really, really huge. And imagine that you have to consider a million images, the data is just going to like blow up. So the pooling layer just helps to reduce the dimension. But at the same time, the pooling layer is making sure that you're not losing information. In as much as we want to reduce the dimension of data, we don't want to throw away a lot of information. So the pooling layer tries to do that and just reduces the dimension. So once we've had like the image processing done, we can just pass it to the pooling layer, and this fully connected layer is what I've explained so far is It's something we're more familiar with. So here you would have your like your typical hidden layer. You can have more than one fully connected layer. You can have like whatever activation functions you want within those layers, sigmoid, relu, and whatnot. And you have your final output, whether it's a dog or not a dog. Again, I don't want to go too in depth into. I just wanted to, bring to our attention, the different models, the different neural networks that occur for different tasks. So that's for convolutional neural networks. There's also the recurrent neural networks, which is specially designed for sequence data. So there's some data that requires um, sequence, like you need some elements, you need to preserve like the way the data is sequenced, right? For image, maybe not so much, but think about speech, for example. For you to understand what I've been saying at the end of a sentence, you need to understand the previous words, that came before the end of that sentence. So that sequence is very, very important in determining the final output. And it's important for natural language and for speech. So RNNs or recurrent neural networks application, they are suitable for tasks where the order of data is important. Language modeling, time series analysis, speech recognition. And this is the way recurrent neural network works. It's a little bit complex, but just think of it the way we have at the bottom here, the green text is basically like your input layer. Think of it as your input layer. So here you can have like, let's say words. Let's say you're trying to predict maybe the sequence of the word, if it's correct or not. You can have like first word, second word, or first sentence, second sentence, third sentence. But in this case, you can use the word. So let's say XT is for word. This is the next word, second word, and third word, right? So you have like this whole complex architecture where you can take the inputs of your data, pass it through this hidden layer. This is the hidden layer. So you can see this is more, it's more horizontally aligned. The neural network we're dealing with so far has been vertically aligned, but this one is horizontally aligned. So you have the input at the bottom layer, you have the hidden layer, and the final output. So you can see this T+1 is just referring to, it's taking into account the input from the previous layer. Like there's some information that is being preserved, because remember that sequence, we need to preserve the sequence or the order of the data. So at the next step of the network, there's like a memory element to it. Like we're able to remember what we saw in the previous um hidden layer. Like we need to take note of that information. So that's why it's written at T+1. So you have the prediction at T+1, prediction at T+2, and prediction at T+3. So you see how this works here. So there's an example here trying to determine if the word audacity, this is a sequence prediction, right? So I'm trying to see if there's like a sequence of the word that makes sense here. So you can see U, G, U. So for U, the output is 0.2. For G, output is 0.2. U is 0.18. I can see that as we are moving across time, time T, you can see that it's slowly increasing as the name starts to make sense. This is audacity. As the name starts to make sense, 0.24, 0.25, 0.23. And at the end of the sequence, we have a very high value, right? So this to say that, okay, if I look at the marks of this, right, wherever this stops, I can say, okay, I'm able to identify like a sequence in the data. I just try to simplify this just to get the concept across, but to understand it, much better, you need to understand like the architecture of the recurrent neural network and how it works. But this is just to demonstrate just a very simple example of a sequence prediction. So I'll just again take a very quick stop here. Just quiz. Mention two applications of CNN and two applications of RNN in the chat box. So we'll just I think take like 5 minutes break. So we'll just move to the next section of this. So this will take too long. This is the concluding section. Just Let's talk about deep learning. You said a lot about perceptrons, deep learning, neural networks. So just to bring it back home, data science. At the end of the day, right, whether it's machine learning, deep learning, AI, data science, kind of, I think there was a chart here that I want to share. I think I forgot to highlight that. Yeah, so if you look at this diagram here, you can see, in the very inner subset, there's deep learning. In the larger umbrella, there's machine learning. There's artificial intelligence, which is kind of like the holy grail of everything. But here you have data science, which is a much more broader field. Or it's a much more broader field that requires deep learning, some knowledge of deep learning, some knowledge of machine learning, some knowledge of artificial intelligence. So at the end of the day, we might not all get to work maybe very, very deep into deep learning or very deep into machine learning or very deep into artificial intelligence. But since data science is kind of like an umbrella field for these fields, all of these things are very applicable in data science. So the last section of this presentation is just to bring everything together and say, okay, how can we take advantage of this technology? When we're working in data science, how is this useful? How should we approach this kind of problems? So what role does deep learning have to play in data science? So, like I said, deep learning is there's some problems that you can use, regular machine learning, traditional machine learning, and solve those problems. And I mean, roughly that accounts for like 50% of the problems that, currently you would face. But there's also like unsolvable problems that would need neural networks. So think about image recognition, natural language understanding, and whatnot. And those form like a relatively tiny percentage, about I think 5% of the solvable problems. So when you're in a data science environment or you're trying to solve problems with data, I think from this it's like a 50-50 thing where data 50% of the time data science is able to solve your problem. But 50% of the time data might not be able to help you. What they've said is like 45% of the time you can use your regular machine learning for it. But there's 5% of the time where your regular machine learning might not work. And deep learning, you have to employ deep learning. So it's important to think about this when you're faced with solving a problem. You don't just jump straight into like deep learning. You first have to think about the problem deeply and say, okay, can we actually use regular machine learning model for this? And if your regular machine learning model will just fail, then you can just move to trying out deep learning methods. So sorry, that's what the solving data science problem, deep learning. So when you come up against like some ML problems that requires some sort of human interpretable characteristics of data where um, as a human being, you can look at the data and try to say, okay, yes, this makes sense. I want to create features out of this data. Ideally, you don't want to be applying deep learning methods for those kind of problems because you as humans, you can already look at the data and create features, do some feature engineering, interpret data and make sense of this before even applying your models or your applying machine learning. So this kind of traditional models like linear regression, logistic regression, or nonlinear features or like gradient boosting or decision trees, they might help you. But if that doesn't solve your problem and you can't manually look at the data and create like features, and you want to improve maybe like some marginal improvements in the performance of a model, then you can go ahead to apply deep learning. It's kind of like experimental in that regard. Yeah, actually, it's supposed to be one more. Yeah, but just wrapping up on this. So, again, deep learning it's new. It promises a lot. It's very complex. It's able to help us in really, really complex problem domains that we as human beings might not be able to interpret the data. So it's great for that reason. But at the same time, we don't want to lose sight of what is important, which is solving problems with tools that we already have that will take minimum effort, or just being efficient with effort and resources. So you have a problem, the first thought should not be, oh, how can I use this really complex solution, which applies to life generally. Like you want to think about the simple solutions first, and if that fails, you want to move on to complex solutions. So for the simple solutions, traditional ML work. If it work, then perfect. If not, you are free to try out deep learning. Given how complex it is, it might be able to solve your problems, but like the previous slide showed, these are like 5% of the time. So yeah, that's just like a final, I would say, word of caution to trying to understand how to apply deep learning for data science problems. And this brings me to the end of this presentation, I think. And I've attached a couple of references here that were useful for the presentation. So one recommendation I would give here is the deep learning specialization on Coursera is very, very solid material, and it's pricey, but you can apply for financial aid, which they typically give. You just need to be able to prove that you can afford it, and they would be sure to give you a very, very good discount off payment. So I would totally recommend that. Just reading up on articles, taking courses that relate to deep learning would go a long way. And yeah, I hope this session was helpful. I hope it provided like value to everyone here. I hope we're able to get as much. And again, it's supposed to be a building block. So this is not the whole picture, but I think this is a good place to start. And you can explore other courses, and maybe incorporate this into like your project if you are comfortable enough. Um, yeah, this is the end. Thank you everyone for your time. Really, really appreciate this.